Okay, so let's talk about a new and different type of bonding here, and that's going to be covalent bonding. But first, a little bit of review. You need to take some notes or have this in your head. First of all, what does it mean to be bonded, and what is this concept of ionic? Remember that bonding is two or more atoms that are chemically combined to help each other satisfy the octet rule. Ionic bonding is when one atom gives electrons and the other atom takes. One becomes positive, one becomes negative. They become ions. And ions have opposite charges, and opposites attract, so they get stuck together. This is something like sodium with its one valence electron, chlorine with its seven. And we can see what happens here. These two can get together and help each other out. This guy gives his electron to chlorine. Now chlorine has a -1 charge because it's gained one electron. Sodium now has one more positive charge than negative charges. Well, these two things are now stuck together because opposite charges attract. And you have the compound sodium chloride. That's what's called an ionic bond. When one atom gives and the other atom takes, that makes an ionic bond because the elements become ions, they become charged things. And then those charged things attract oppositely charged things and they stay stuck together. They make the compound. They are bonded that way. So, this is what we've been doing the whole time. We've been doing ionic bonds, which are things of opposite charges. Primarily, ionic bonds are metals, stuff over here, and nonmetals. We've got metals and nonmetals that tend to make ionic bonds. Okay. And that makes sense because metals want to give electrons and nonmetals want to take electrons. So this makes sense. This is all the formation of ionic bonds. But there's actually a different type of bond out there, and it's called a covalent bond, in which the atoms get stuck together, but by a different method. So let's look at an example. Let's take boron here. Boron has 3 valence electrons, and boron would love to get rid of 3 valence electrons to satisfy the octet rule. But notice boron is on this side of this stair step. Boron is a non-metal. Even though it's going to try to give 3 electrons, it's still classified as a non-metal. Well, let's pair that up with fluorine. Fluorine, let's say, wants to take 1 electron because it has 7 valence electrons. It's going to want to take 1 to satisfy the octet rule. Now, boron is a pretty small atom, only has 2 energy levels. So its electrons are pretty close to the nucleus. I mean, the second energy level, here's the nucleus. There would be 1 energy level. There's 2 energy levels. Boron's 3 electrons, its 3 valence electrons, are pretty close to the nucleus, meaning they're held onto pretty tightly because those electrons are still pretty close to the protons in the nucleus. And this makes a difference. So I've got boron with my 3 valence electrons. And then I've got fluorine with the 7. And we can see how this is going to work. We would think boron wants to give up an electron to fluorine that way. Boron give up an electron that way. And boron give up an electron that way. Now it seems like everybody's satisfied the octet rule. And yet we have, but here's what's different. Boron really can't give electrons because the atom is so small and these electrons are so close to the nucleus because they're only in the second energy level. Boron holds on to its electrons very tightly. Even fluorine, which is the biggest electron bully out there, the most powerful atom at coming in and grabbing electrons from somebody else, is not strong enough to totally take the electron from boron. So we've got a conundrum here. Fluorine desperately wants that electron, but it can't take it from boron. Boron really would like to give it up, but it can't give up the electron because its protons hold on to those electrons so tightly because they're only in the second energy level. So they come to a little bit of a compromise here. Fluorine looks at boron and says, hey, why don't I kind of like borrow this electron? I know I can't take it from you. I'm not strong enough to totally grab it from you and pull it away. But what if I just kind of like scooch it over here close to me? It's still yours, and it's still being attracted by your nucleus and your protons, but I'm just going to pull that little electron over here, and we'll kind of share it. And boron's like, okay, that's the best case. That's the best option that it has to satisfy the octet rule. So what we have here going on is a set of atoms that are now not giving and taking electrons. What they're doing is they are sharing electrons. Sharing electrons is what we call a covalent bond. Remember, an ion is something that's charged, so something gives and something takes an electron. A covalent bond is when, the one guy can't take the electron from the other, so they play a little tug of war and they end up sharing the electron. That's what a covalent bond is. It's just when two atoms are sharing a pair of electrons. Now, the thing is with these covalent bonds, they don't share all of the electrons. Notice fluorine's not sharing these over here. It's only sharing this one. What we have here is called a lone pair. We have 3 lone pairs. These are pairs not shared. So fluorine only shares this one, and fluorine has a couple other sets of electrons that are not shared, and we call those lone pairs. They are pairs of electrons, but we're not sharing those with boron. We're only sharing these two right here. So how is a covalent bond different than an ionic bond? In an ionic bond, electrons are given and taken. In a covalent bond, electrons are shared between two atoms. That's the difference. Covalent bonds are sharing, ionic bonds are giving and taking. When we name these covalent compounds, we use a little bit different type of nomenclature because it's not the same rules for ionic as we're not giving and taking. The formula here ends up BF3. We got 1 boron and 3 fluorines. This is where we're going to start to use what you saw before, our prefixes, where we use a number to denote, a prefix to denote the number of atoms of that element that are in the compound. So the prefix for 1 is mono, like a monocle. It's like a one lens piece of eyewear. As a bifocal is 2 different lenses, and a tricycle is 3 wheels. So we're going to use the prefixes mono, di, tri, tetra, penta. We have all these prefixes that tell us the number, but there is convention to doing this. If the first element is 1, there's one of them, all we have to say is the name of the element. We don't have to say monoboron. It's just boron. But we need a prefix to tell us how many of the second one. This would be boron trifluoride. So the rules for naming. 1, you're going to name the first element. You say boron. 2, Name the second element. Boron and fluoride. Now, rules 3 and 4 is about the prefixes. No prefix if the first atom is 1. Like in this case, we had 1 boron. We don't say monoboron, we say boron trifluoride. For the second atom, so the prefix in this case was the 3 prefix, the tri, so we say boron trifluoride. Let's do another one. Keep in mind, these are going to be generally 2 sets or 2 elements that are non-metals. If it's a metal and a non-metal, they're going to give and take. But if we get 2 over here on this side, as well as hydrogen, because hydrogen acts a lot more like those guys, we're going to use those prefixes. Most of you know what that compound is. Say the name. You know that's carbon dioxide. You remember from biology. There's only 1 carbon, so we don't say monocarbon. We just say carbon dioxide. We use the prefix di because there's 2 oxygens versus that, which would be carbon monoxide because there was only 1. We still don't use the mono for the first one. Sulfur trioxide. Okay. So you're going to be given this list of the different prefixes. You just have to know when to use them. Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, and octa is 8. So you need to have these someplace handy to be able to reference when we start trying to name these. In your first bit of practice is you're going to be asked to name these different compounds, and or you're going to be given the name and you've got to write the formula. And the formula of how many of each one there is going to be told to you by whatever prefix is with that element. So think about this element here. Here we've got 2 nonmetals. We've got hydrogen and oxygen. And how would we name this? And don't say water. Technically speaking, we would say dihydrogen monoxide, because there's 2 hydrogens and there's only 1 oxygen. Now, one thing about this sharing of electrons, isn't always equal. These guys are playing tug of war on a pair of electrons, and sometimes the sharing is not equal. We'll consider hydrogen, and then we got oxygen in between. What happens with hydrogen and oxygen when these 2 guys are fighting over these electrons, turns out they're playing tug of war. One of them is a little bit stronger than the other. So the negative electron ends up being a little bit closer to oxygen than it does to hydrogen. It's kind of like they're playing tug of war and they're going back and forth. The electron kind of spends more time over here. So if we looked at water as a molecule, generally it seems to be a little bit more negative here, which means it ends up being a little bit more positive there. And we call this a polar molecule. A polar molecule means electrons are not shared equally. So you wind up with some more negative times in one place of the atom than you do in the other. Now, as you can imagine, a nonpolar molecule means electrons are shared equally. And the electrons stay exactly in the middle, and there's no separation of charge. The molecule doesn't have a positive end and a negative end. It is entirely electrically neutral because the electrons are being shared equally. Now, this is going to be a big deal later on, and we're going to kind of circle back to this, and it's going to really help us explain how some compounds behave. And we introduce it now because it makes sense, because we're talking about this giving and taking and sharing of electrons. So for now, we just need to realize that, like water is a very polar molecule. It has a positive end and a negative end because the electrons get pulled a little bit closer to one atom than the other. So one part of the atom tends to be more negative, and the other end, or ends in this case, of the atom tend to be a little more positive. So it's kind of like you have like a little weak battery, with its plus and its negative sides to it. And that's going to determine a lot about how that molecule behaves. And a very important thing that we look at a little bit later on down the road. Now, to piggyback on this whole sharing idea, we need to talk about this special circumstance called the diatomic molecule. Now, we know that di means two. This means atoms. And a molecule is just some combination of atoms that are sharing electrons. Sodium chloride is not a molecule. Not a molecule because somebody is giving and somebody is taking. Water is a molecule because they are sharing electrons, not giving and taking. So we've got a two atom sharing thing going on here. And let me show you how this works. We'll take oxygen. Oxygen 1 and oxygen's brother over here. So oxygen and oxygen are bebopping along down the street, and they bump into each other and say, hey, dude, can you help me out with the octet rule? And this oxygen says, I ain't giving you any electrons because I want to take two. This oxygen says, I'm not going to give up electrons because I want to take two as well. So they look around, and there's nobody else around who's willing to give electrons, and they come to an understanding and say, hey, dude, so long as we're just hanging out here together and we really want to help each other satisfy the octet rule, why don't we share? And we can help each other out. And look what happens. They share those two electrons, and they share these two electrons. So now if we think about this oxygen, he has 1, 2, 3, 4, 5, 6, 7, 8. It's like he has 8 valence electrons. Look at this guy. Now he's got 1, 2, 3, 4, 5, 6, 7, 8. He's got 8 valence electrons. So we've got a pair of happy oxygens here because they've satisfied the octet rule. Now notice, this is not a chemical compound. This is not two or more atoms that are making something new. This is two of the same atom. So this is what we call a diatomic molecule. These are two atoms of the same element that will get together and share electrons to satisfy the octet rule, and that makes them stable. Now, out there in nature, you will never, ever run into a single oxygen atom in nature by itself. Oxygen always pairs up with itself to make itself more stable. Oxygen is found as what's called a diatomic molecule. And there are a couple of atoms that do this to make them more stable in nature. Now, if I had some oxygen a container of oxygen, and all of a sudden I threw in some sodium, these oxygens are going to split apart, and they're going to say, see ya, and they're going to go steal electrons from the sodium. But there's not always somebody around who's willing to give up electrons. So long as they're just by themselves, oxygen is found as what's called a diatomic molecule. Oxygen in nature is always that. And there are, I think, 7 elements that do this naturally. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. These are the 7 elements that are never found alone in nature. They are always paired up with themselves because it makes them a lot more stable. And once again, as soon as I throw in somebody else to the mix, like a sodium who wants to give up electrons, these diatomic molecules are going to split apart, and they're going to go and steal electrons from the sodium. But that's not always the case. Sometimes there isn't anybody to take electrons from, so these elements will pair up with themselves to make themselves more stable, and that's called a diatomic molecule. All right, so what I've been drawing for you here is what we call a Lewis structure, or at least the start of it. A Lewis structure is a way to show how the electrons are being shared amongst atoms and how they bond together. I'm going to take, for example, phosphorus with its 5 1, 2, 3, 4, 5 valence electrons. And I'm going to pair phosphorus up with his buddy hydrogen. So hydrogen and phosphorus get together, and because hydrogen is so small, hydrogen doesn't give up its electrons. It's really hard to take the electron from hydrogen, so it has to share. So hydrogen and phosphorus share these pairs of electrons. Now, if we look at phosphorus, 1, 2, 3, 4, 5, 6, 7, through sharing, phosphorus has 8 valence electrons, which makes him very happy, makes him stable, satisfies the octet rule. Hydrogen, as you can remember, only has 1 energy level. So hydrogen is kind of full. It's stable with 2 valence electrons. And by sharing with phosphorus, we see that, well, that hydrogen now has 2. That hydrogen now has 2. And that hydrogen now has 2. So everybody's happy through sharing. Now, this gets kind of cumbersome drawing all these dots and such. So here's what we do. We draw what's called a Lewis structure, where instead of showing a bond being these 2 electrons like this, we draw a line. This is a Lewis structure where the line represents a shared pair of electrons, and that's why these guys are stuck together in the first place. Notice that phosphorus still has what we call a lone pair of electrons. So each line is a shared pair. So that's 2, 4, 6, 8 electrons around phosphorus satisfy the octet rule. So these Lewis structures are just a way to show how the electrons are being shared amongst a group of atoms. Let's look at another very common compound of carbon dioxide. We know there's 1 carbon and 2 oxygens. Carbon going to share electrons like that and share electrons like that. Then carbon's going to share like this and share like that. Now we've got 4 pairs of share. We've got 1, 2, 3, 4, 5, 6, 7, 8 share. By sharing, carbon now has 8. Oxygen, 1, 2, 3, 4, 5, 6, 7, 8. By sharing makes oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Everybody's happy. Now let's draw the Lewis structure for this. Notice now Remember, each line is a shared pair of electrons. Well, I've got 2 shared pairs between this carbon and this oxygen. Now, with these Lewis structures, I've got to show all these shared pairs, and I also have to show all the lone pairs. So oxygen has these 2 lines going to carbon, 2 shared pairs, and then 2 lone pairs, which I still show. And this is the Lewis structure for carbon dioxide. Notice carbon doesn't have any lone pairs of electrons. All of carbon's electrons are being shared with oxygen. So there are no lone pairs. But now, let's count for carbon. Remember, each line is a shared pair. So there's a pair, 2, 4, 6, 8. So we've got 8 electrons around carbon. That works. That satisfies the octet rule. These are Lewis structures, which show how the electrons are shared between atoms. Notice here we've got 2 shared pairs between the carbon and the oxygen, whereas over here we only had 1 shared pair. We denote these differently. When we have 1 shared pair, we call that a single bond. This over here would be a double bond. And you can even get a triple bond. You can sometimes have this. Atom X and atom Y can have 3 shared pairs of electrons between them, and that's what's called a triple bond. When there's 3 sets or 3 pairs of electrons that are being shared between 2 atoms. And you'll see some examples of these when we do our practice work with this. Okay, so what do we do now? Well, at this point now, you're going to finish with these notes, and you're going to go to your assignments page, and you're going to open up the assignment that has your practice on naming covalents, doing the formula mass, and the atom counts for various compounds. This will be due tomorrow, and it will be reviewed in class.